Let's talk about molecular geometry. Now, most people understand the geometry of molecules in two dimensions because you can just draw out the shapes on a piece of paper, so it's easy to visualize. But this gets a little bit more difficult in three dimensions, so that's why I'm going to be explaining that today. This may seem like a very narrow topic because atoms are measured in billions of meters, but there are various applications of this to some of the hottest topics in science right now. So let's go ahead and get right into this. Let's start off with what is regarded as one of the craziest phenomena in science, which is that particles such as electrons in an atom or photons of light can also be described as waves depending on the context. This idea is more thoroughly researched in the field of quantum mechanics, so if you're interested, make sure to check that out. Anyways, the longer the wavelength of a wave that a particle corresponds to, the less energy the particle has. This is because waves oscillate or move up and down as time moves forward. So the more change that occurs in a wave over a certain distance, the more energy it is carrying. Let's say that I take very large steps, but my randomly appearing twin here takes very small steps. Who gets more tired, or in other words, who exerts more energy? Well, my randomly appearing twin exerts more energy, therefore, waves with smaller wavelengths correspond to higher energy particles. If I draw two parallel lines to signify the beginning and end of a wave that repeats itself between the two lines, and a central axis for the wave to move up and down about, what is the lowest possible energy wave that could be drawn between the two lines that would not cancel itself out? By the wave canceling itself out, I mean that if a wave were drawn like this, and it was to keep repeating itself between the two lines, destructive interference would cause the wave to cancel itself out. To remedy this, the wave should touch the central axis at both the beginning and end, making a wave that does not interfere with itself. Now, as far as we know, the lowest possible energy of a wave would be the wave with the longest wavelength, so basically, looking sort of like this. Since this wave corresponds to the lowest energy particle found, or in terms of molecular geometry, the electron with the lowest energy, and the electron orbital with the lowest energy, is closest to the nucleus because it takes energy to pull negative electrons farther away from the positive nucleus. This is the first electron orbital. But wait, this has to be measured in 3 dimensions, since real life occurs in 3D. So we have to revolve this 2-dimensional wave around the central axis, which makes our first orbital a sphere. Our next orbital would have the next lowest possible energy, meaning it would simply have to touch the central axis at 3 points instead of 2, to make the next longest possible wavelength. If this was revolved around the x-axis, it would make a dumbbell shape. These so-called electron clouds keep going on with the number of intersections with the central axis that shorten the wavelength and make higher energy orbitals. But what is essential to our understanding now is how molecules shape themselves with these electron clouds. Electron clouds from different atoms overlap to share electrons because neither of the atoms coming together had enough electrons to have a stable structure or shape in the first place. The shared pairs of electrons that hold molecules together are called covalent bonds. VSEPR theory, or valence shell electron pair repulsion theory, helps us determine how molecules are shaped based on how many electron pairs they have. I know this theory sounds complicated, but it's basically stating that all of a molecule's electron pairs, which come in 2 types, repel each other because electrons have like charge, but still stay attached to the nucleus. The first type of electron pair is the covalent bond. Covalent bonds get as far away from each other as possible because they're all just shared pairs of electrons repelling each other, but they still stay attached to the central atom. For example, in carbon dioxide, 2 oxygen atoms are covalently bonded to the central carbon atom, and spread out as much as possible while still staying attached to the central carbon, making 180-degree bond angles. The oxygen atoms do have lone pairs of electrons, but lone pairs of electrons do not influence the molecular geometry unless they're on the central atom, which brings us to the second type of electron pair that influences molecular geometry: lone pairs of electrons on the central atom. These occur when the central atom can't make enough covalent bonds with the atoms around it because the atoms around it run out of electrons to share, so the central atom needs lone pairs of electrons for a stable structure of electrons around it. Lone pairs of electrons are like ghost covalent bonds. They exert a stronger repulsive force than regular covalent bonds, but they aren't actual bonds, so they don't count towards the molecular geometry. For example, in water, the 2 lone pairs make the molecule seem 4-sided or tetrahedral, but it's actually just called bent because the lone pairs don't count toward the geometry. Now I'll explain the applications of this. Starting with the biological aspect of things, gene editing requires you to know the shapes of the receptors on the outside of cells so you can send your device in to edit the DNA of the cell. Now let's think big, by which I mean traveling outside of our solar system. One of the prospective methods of doing this would be to make a sail that moves forward when light from the sun bounces off of it. In order to make a good reflective surface, you want something with a flat structure for light to bounce off of easily, such as carbon dioxide. As you can see, the applications are endless, so if you've learned anything from the past 5 minutes, it's that something small can make a big difference.